Hello everyone, welcome to this video. In this video we'll be looking at another result which tell us about the generators of finite cyclic group. So knowing one generator, can we have others, and how and what is the procedure for that? So let's move ahead and see this thing here. So suppose the order of any element A is given to be n, right? This is given to us. Then the result says that if we have the subgroup generated by A is equal to the subgroup generated by A to the power j, right? In this thing is possible if and only if the GCD of j with 1, right, by j with n. And what is n? N is the order of the given element A, right? The GCD of this j with the order of this element n, that should be equal to 1. And moreover, the order of A is equal to order of A to the power j if and only if the GCD of n with j is exactly equal to 1. So this is the result here. Now for the proof of this result, that is very simple because we already know this result, right? So in this result, if we take I as equal to 1, in that case the GCD of n with 1, that is going to be 1. So you see we have the result very quickly, because if we replace this I with 1, so we would have the generator, the group which is generated by A equal to the group which is generated by A to the power j. This thing would be there if and only if the GCD of n with I, which is 1. So 1 is equal to GCD of n with j, and this is what we wanted to prove in the first part of this result. For the next part, if we again take I as equal to 1, so this thing would become the order of the element A. If the order of the element A is equal to the order of the element A to the power j, then we have the GCD of n comma 1, that is n with I, that is 1 only, so 1 is equal to the GCD of n with j. So this is what we wanted to prove here in this case. Okay, so moving further, after the proof, let's see where and how can we utilize this result. So the power of this result is that once we have one generator of the cyclic group, all other generators can be found, and this is only done when we have cyclic finite group with us, right? So all these results that we are studying about, they revolve about cyclic finite group. So you should keep this thing in mind and should not generalize the results. Okay, so how this is done? Once we know a generator, all the other generators are calculated. For example, suppose we are taking the group D6. Now this is a group of rotations of hexagon, right? So hexagon has 6 sides, so that means if we divide 360 by 6, so we have the angle of rotation as 60 degree with us. So that means the member of this group D6, they would be R0, that means rotation with 0 degree, R60 rotation with 60 degrees, R120 rotation with 120 degree, R180 rotation with 180 degree, R240 rotation with 240, and R300 rotation with 300 degrees. And next one would be R360 degree, which is equivalent to R0 degree, right? And so on. The next angles would be then R480, R420 would be equal to R60 only, R480 would be equal to R120 only, and so on, right? Because we have this group as the group of rotation, and this is a cyclic group, and after certain period of time, all the entries, they repeat themselves, and we have finite number of elements within this group, hence this is a finite group. So we know one generator here, which is R60. By R60, we can generate all the elements of this group. How this is so? Let's see. If we take R60 to the power 1, that is R60 only, so we have this element, right? If we take R60 to the power 2, so that means we are applying this operation 2 times. So we are firstly applying R60 and then we are also applying R60. So we are rotating this hexagon by 60 degree first and then by 60 degree first. So in total we are rotating it by 120 degrees. So this is R120. So we have the second element with us. Then we have R60 raised to power 3. So we are applying this operation 3 times onto the given hexagon. So after 160 degree, after another 60 degree, we are also rotating it through one more degree. So basically 60 plus 60 plus 60, that give us 180 degrees. So in total we have a rotation of 180 degrees, so that is R180. So this comes the third element here. Next, let's take the power 4. So we have to rotate the hexagon 60 times by 60 degree 4 times, so that means we have R240 with us. And next, so we have this next element as R240. Next we have to apply this operation R65 times, so this gives us R300, like the same result. And when we rotate it 6 times, so we would have R360, and R360 is basically R0 degree, right? So rotating it through one complete cycle, or not rotating it at all, so that is the same operation, because all the vertices, they would be the same in this case. So in this case we have R0 also. So you see, by this R60, by taking its power and repeatedly applying this operation, we obtain all the entries of this group D6. So that means this R60 forms one generator for the group D6. So moreover, we can say what is the order of this group element R60. So here you see the element of this group element R60 degree, that is given by 6. Why? Because if we take R60 to the power 6, we obtain R0, which is the identity of the group, right? So this is one thing. Another thing, how we can obtain other generators of this group. So we can make use of this result here. So once we know about one generator, all the other generators are obtained. So that means we are interested to calculate what is the power j here, right? Once we know different values of j, we would have different generators. So for that, we can make use of this thing, that GCD of n, which is the order of this element A, right, and j, that should be equal to 1, right? So using this thing here, the GCD of the order of the element, which is R60 in our case, right, its order is 6. So we have 6 here. We wanted to calculate j, and the GCD should be equal to 1. So what all numbers are there with us? So we either have 1, 2, 3, 4, 5 and so on. So taking the power 1, the GCD of 1 with 1, so it is obviously 1. So R60 raised to power 1 is one generator, which is R60 only. That we already know, right? 2 is not a generator because the GCD of 2 with 6 is not 1, but it is 2. 3 is also not a generator because the GCD of 6 with 3 is 3 and not 1. 4 is also not a generator because the GCD of 4 with 6 is 2 and not 1. 5 can be there because the GCD of 6 and 5, that is equal to 1. So therefore the other generator that we have is this element raised to power j, which is 5. So you see R60 raised to power 5, this one is R300. So in this case you have R300 as another generator. So in this case actually you can do the calculation by just looking at the power of all the elements. So this could be done in this case, but it is not feasible in many cases where we have different examples and lot of calculations are involved. So therefore this result is quite useful there, right? So we'll be looking at another example of this thing in the next video. Well, that is it for this video. Thank you for watching.